In this video, I will talk about the modified Euler's methods, which is a numerical method that combines ideas of both explicit and implicit Euler in order to solve initial value problems. So let's make a short recap of what it means to use explicit or implicit Euler in order to solve such an initial value problem. So let's say that we want to solve this problem over here. dy dx is a function of x and y, and we have as an initial condition that the function that we're looking for at x is 0 should be equal to 1. In this case, let's say that we have an exact solution such as this, and the direction field is according to the gray arrows over here. So let's take a look at how both explicit or forward Euler and implicit or backward Euler would go to work over here. And let's assume that we want to make a graphical interpretation of these methods by using an h of 0.6. So this means that, well, we start from this initial condition, and we want to land somewhere along this line over here. That is where the next step is, where our next numerical solution will lie. Now, let's start with forward Euler. And let me, for forward Euler, use, let's say, orange. So forward Euler, what it does is it will update the solution based on the direction field evaluated at the current solution. Okay, so how does that look in the figure? Well, that means we evaluate the direction field, and in this case, this corresponds to a horizontal line, and we see where this horizontal line crosses this vertical dotted line, where x is equal to 0.6. So this is our explicit Euler solution. Let's call this x2 EE for explicit Euler. Now, how about implicit Euler? Okay, implicit Euler, let me draw that in green. Implicit Euler or backward Euler actually evaluates the direction field not at point I, but at point I plus 1. So this actually corresponds to also drawing a line which has to be which has the slope corresponding to these gray arrows over here. But it's not evaluated at step I, but at step I plus 1. So what we actually need to do is, instead of looking forward using current information, so here we used current information and projected it forward, what we do here is we look at the new time step already and check where is the point such that if we draw a line which is tangent to the direction field, that we end up back in this in our current solution. So that is backward Euler. That's why it's called backward Euler as well. And let me try to draw this. So this is obviously harder because this does not allow you to explicitly formulate that solution in the next time step that mathematically corresponds to having to solve this difficult equation. And it also makes it harder for me to draw because I have to do some guessing over here. But let's say that if I draw the tangent line somewhat approximately like this here, if I look at this line over here, well, we see that that at this point, if this were to be the implicit Euler solution, that it corresponds to this equation for backward Euler, because we see now that this equation is fulfilled. So we use the slope at the new value for x such that this formula holds. So that is what backward Euler does. It actually looks backwards, whereas forward Euler actually looks forward. Now we see also here that whereas explicit Euler underestimates the exact solution in this case. Implicit Euler tends to overestimate the exact solution in this case. And whereas explicit Euler only uses information from step 1, implicit Euler only uses information from step 2. So ideally, we should be able to combine both those sources of information to come up with a method which is better, let's say more accurate and more usable in practice. And that's what our aim is in this video, is to try and find a numerical method that combines both explicit and implicit Euler, such that we can take into account that this direction field, that it varies between 0 and 0.6 in here. So just writing down the equation. So we have for this ordinary differential equation, we have that explicit Euler reads as follows, implicit Euler reads as follows. So what would happen if we just add the two of these and divide it by 2? Well, then we get what is called the trapezoid rule, and that's completely analogous to the trapezoid rule for a numerical integration. This is a valid numerical method for solving ordinary differential equations. We will not go into more detail on the trapezoid rule here in this course, but a downside of the trapezoid rule is that it is still implicit, as you see over here. So still we have this drawback of implicit Euler, where it is intuitively hard to draw this on a graph, but it's also mathematically hard to find the solution yi plus 1, because again, we would have to solve a nonlinear equation within every single step. So let's see whether we can find a workaround in order to get rid of this implicitness, let's say. Now we can do so by splitting the integration of the ODE within that step into 2 sub-steps. So what we do first is we take a explicit Euler step. From step I, we just extrapolate according to the current slope. So that will give us a, let's say, a preliminary solution y star. And at that y star, we compute the slope. So this y star is already an approximation for the solution at step I plus 1, although it's not, it's just an explicit Euler approximation. So we want to do better than that. But what we actually do is, well, we also incorporate how f behaves at xi plus 1 and at y star. So by doing this, we are able to incorporate more information on the function f in constructing our numerical approximation of the function y. In this slide, I just rewrite this a little bit, as you will in textbooks generally see modified Euler more commonly denoted like this. It's simply this y star directly substituted into that equation. So it's a bit more compact, but is less clear in my opinion. So by writing it out in 2 separate steps, it becomes much more clear what you're trying to do. So first we compute this preliminary solution, which we only use to evaluate f at xi plus 1 and at y star. Now let's look at an example where this really comes to life. So we are revisiting our initial example over here. So the initial value problem, where we have that the derivative of y is equal to x times y, and we have the initial condition of that y at 0 should be 1. We already mentioned that the exact solution has the following form. So that's y of x is e to the power x squared over 2. And we looked at how explicit and implicit Euler behaved for this kind of initial value problem. Now let's take a look at how modified Euler does. So we will do this for a step width of 0.4. And recall that modified Euler consists of 2 sub-steps within each step. So first we compute this preliminary y star based on a simple explicit Euler formula. And then we compute the our let's say, our final numerical solution by averaging these two slopes. So the f evaluated at xi and yi, and then also at xi plus 1 and y star. So let's take a look at what this looks like in practice. So first we take our first step. So that is this kind of Euler step. So we evaluate the slope at the current solution, and we extrapolate that outwards over a distance of h, so to 0.4. And that leads us to this star symbol, which is located at xi plus 1 and y star. And now using this star value over here, that is the exact point where we will again evaluate the function. And this function evaluated, that will again give us a slope where this slope at this point corresponds to this other purple dashed line. And then we will take the average of those two lines, so the average of the slopes of those two lines, in order to actually update the solution. And that's what we get over here. So this solid purple line is then the average of the two. And then wherever this solid line crosses the point where x is equal to 0.4, so this vertical line I'm tracing right now, that is where our solution will be in the next time step. Okay, so that was one complete modified Euler step, and we can keep repeating this until we reach the desired interval for x. So again, what we do is, well, we take basically an explicit Euler step, let's say. So we evaluate f at the current solution, which gives us this this dotted line as a slope, and then y star is defined as where this dotted line crosses the point where xi is equal to 0.8. That's 2 times h. So that's over here. And then at this y star, so at this point xi, in this case x1, x2, x3, y star, we again evaluate f, which will give us a second slope, which we can also draw. We take the average of the two, and that leads us to this new numerical solution. We repeat the procedure, so taking the local slope, taking the slope at this star point over here, which gives us this line. We take the average, and that will lead us to the following. Again here, local slope, we also evaluate the slope over here, which is this line. The average of the two is the solid line, and then the modified Euler step will reside over there. And you see that by doing so, we incorporate information both from the start and the end of every interval. And this, well, at least from a qualitative point of view, this leads to a fairly accurate solution for modified Euler, is what we're observing over here. So let's make a short qualitative comparison of Euler's methods that we've seen so far. We saw for this specific initial value problem with the exact solution of e to the power x squared over 2, we found that explicit Euler grossly underestimated the error, the solution, sorry. Implicit Euler grossly overestimated the solution, whereas modified Euler lies nicely between explicit and implicit Euler. Also, if you do an error analysis on this, well, in the previous video, I showed you that explicit Euler is first order, but also implicit Euler can be shown to be of first order accuracy, whereas modified Euler is second order accurate. So that's already looking like a somewhat more accurate method over here. Now, I've been talking a lot about explicit and implicit Euler and trying to draw this all in some graphs. But I think it's important that you are able to see how easy and straightforward it is to implement these methods in MATLAB, because that's hopefully makes the mathematics and the graphics come to life a bit more when we apply it to specific numerical examples. And that's what I will try to do in the following slides. I will implement explicit Euler, implicit Euler, and modified Euler in MATLAB for this initial value problem that we've seen already quite some times. Now, there are other methods that we will see later on in this lecture. I'm not going to implement them in MATLAB all in these video lectures because otherwise things get very long videos, and I think they're already quite long. But it's very analogous, and you can try to do this yourself. For instance, when we look at midpoint or at Runge-Kutta, I think it's a nice exercise if you try to implement them yourself in MATLAB. So let's have a quick look at an implementation of the explicit Euler method within MATLAB. And you will see that this is rather straightforward. So let's write this as a function, and let's open a new file. So we select new and function, and then out pops this editor window in which we can write our function. Let's first name the function. I will give it a name ODE for ordinary differential equation, and then explicit Euler. And what are the inputs for such an ODE solver? Well, it needs to know what the function is that we're trying to, the right-hand side function of the ODE that we're trying to solve. So that is f. It has to know the starting point for x, that is a, the end point for x. And we also have to provide a spacing for the substeps h and an initial condition y0. And that is basically, if we look at the formulas, that's all that is needed in order to solve an ODE using the explicit Euler method. So the first thing that we do is, well, we define the the points xi, let's call them like this. We have to set the initial condition y0, and then we do an iteration loop from I is 1, which corresponds to xi is a, to I is n, which corresponds to xi is equal to b. Okay, let's give it a go. So we define the points, so we can easily define a vector with spacing h as follows using this colon operator. This defines x as being a vector starting from a up until b with a spacing of h. Okay, so far so good. Well, now we set the initial condition y0 in a certain variable, and let's call this variable y, and this will also be a vector, and we put in there already one value y0, and we will keep adding values to this vector as we loop through the iterations from I is 1 to I is n. So we know that x has n plus 1 entries, so n is equal to the number of elements in x minus 1. And then we do our loop. So we go from for I is 1 to n, and we end our loop. So now what is left for us to do is to program these explicit Euler functions into this iteration loop. And well, these are not so hard, but I will try to program these in a generic way that we can also use them. We can copy a lot of this code when we look at other time integrators, such as implicit Euler or modified Euler later in this lecture. Okay, so let's define xi, which is x at index I. We know y at index I, because that's also something we have computed previously, or in the first iteration loop. Well, we know that this is the initial condition. We have to compute the slope, and then we update the solution to y at index I plus 1, which is y at index I plus h times the slope. And we simply add this y I plus 1 to the vector y itself. So using this every time we append another value to this vector y. Now, specific for explicit Euler, this slope is simply the function f evaluated at xi and yi. So let me check this. Well, what we do, we define x, we set the initial condition, we do an iteration loop, and in each iteration loop we compute the slope based on xi and yi, and we update y to this yi plus 1 using h times the slope. So this seems fine. And then the output that we give back is the vectors x and y. Okay, so let's save this and try it out. Let me close this. So let's say that we want to try this for the function f, which is a function of x and y, fx times y. And we have as an initial condition, or let's just push it into the function directly. So we have ODE explicit Euler that we want to call, and then we will get here indications as to what we have to enter as arguments. So we have our function f, we have our function f, 1 second. We have our function f, which is the first argument. We have a, the starting point of the interval, b, h, and y0. So we input f, which is this function x times y. We integrate starting from x is 0 until x is 2. As a grid spacing h, we will use 0.4, and we will use an initial condition of 1. And let's see what then comes out. And we see that MATLAB replies with these two vectors x and y, which are, if everything went well, the approximations of the function y of x, which is the solution to the ODE that we defined. And let's take a look at this numerical solution, and we can plot it as follows. I will just add some formatting that we use dashed lines, and we put marker points wherever we have these distinct discrete points defined. So we plot it, and we see here that this is the numerical solution to the ODE using this simple programming of the explicit Euler algorithm. Okay, so similarly, like we programmed the explicit Euler algorithm in one of the previous cases or previous slides, let's also try to implement the implicit Euler algorithm. And I will do so by simply copying this file and paste it and give it a different name, ODE implicit Euler, because we will be able to reuse a lot of the code that we have in there actually. Let me save it. Okay, so the inputs to an ODE solver, well, they're not different for implicit Euler or for explicit Euler in that aspect. So we can just keep this skeleton as it is and make adjustments where necessary. So the way we define the points xi, well, that's simply the same as for explicit Euler, and also setting the initial condition remains unchanged. Now, within this iteration loop, we will have to do something different though. We cannot simply use this slope of f evaluated at xi and yi because, well, we would, in order to evaluate the slope, we would need, according to the implicit Euler idea, we would have to evaluate this not at y at index I, but at index I plus 1. So instead, actually, what we have to do is we have to get a different way of computing yi plus 1. And well, we had to do this using this nonlinear equation that we saw in one of the previous slides. So in this nonlinear equation, well, we let's define the equation. Let's call it the equation G, which is a and let's use this auxiliary variable z as the variable in this equation. And well, based on what we've seen so far, we can write this nonlinear equation as follows. So this is z minus I y at index I minus h times f evaluated at xi plus 1 and evaluated at z, where z is a surrogate for yi plus 1. And let's also define xi plus 1 here as xi plus h, or x. Let's make it a bit more formal, xi plus 1. This is a bit easier to read this code. So what we have now here, we have this nonlinear equation of z, and we have to find the zeros of this nonlinear equation in order to find, well, the appropriate z or the appropriate yi plus 1. Now, in order to solve such a nonlinear equation, we saw in chapter 3 many different methods, and I will just use this MATLAB built-in method F0. You could also just use Newton's method or the secant method, whatever you want. I'm going to use F0 because it's very easy to use and it's already programmed for us. So the only thing we have to provide here is a function and an x0, where this x0 is the initial guess that we put in for the zero of this function g. And for this initial guess, well, again, you can choose whatever you want as long as it works. I think a good initial guess, so a good initial estimate for what yi plus 1 would be simply the numerical solution for y at index I, which is yi. So doing this, well, we should be able to compute the zero of this nonlinear function, which is then the numerical solution at index I plus 1, and we simply add it to the vector. So using only minor modifications, we were able to switch from an explicit Euler to an implicit Euler time integration here. And you see that we have to solve this nonlinear equation using an appropriate method. Okay, let's give it a try. We have defined this function f already for this explicit Euler integration, so now we can simply reuse that. So ODE implicit Euler, again we use the same parameters, so the function is f, we start at x is 0, we go until x is 2, we use an h of 0.4, and we use as an initial condition of y0 of 1. Let's see what this gives out. So again, we get back an x, which is the same as this explicit Euler. That makes sense. But we see that our solution, the numerical solution y, is somewhat different. And we can again also plot it. So let's plot it on the same figure, which I still have open here, I think. So this is in blue, we see the solution for explicit Euler. And let's also add to that, so I will hold on. Let's also add to this then this newly defined x and y, which is the solution of the implicit Euler. And we see now here in red the solution of the implicit Euler algorithm for this specific function using this specific grid spacing, etc. Let's now try to implement the modified Euler algorithm into MATLAB as well. Since modified Euler is an explicit method, let me copy this framework that we already programmed for explicit Euler and use that as a starting point for modified Euler. So let me just change the title here, ODE mod Euler. And let's reuse most of the code that we can and change wherever it is necessary in order to convert this current explicit Euler algorithm into a modified Euler algorithm. And when we check the description of modified Euler, well, the only difference is actually in this slope over here. So whereas explicit Euler uses as a slope the function f evaluated at x index I and y index I, modified Euler instead uses an average of two slopes over here, where the first slope is simply the slope of an explicit Euler, so that's f evaluated at xi and yi, but the second slope Well, that is kind of an approximation at what the slope would be at index I plus 1. Now, we won't use xi plus 1 and yi plus 1 because we do not know yi plus 1 at this point in the code. And that would make it an implicit method. And we're looking for an explicit method here. Modified Euler is an explicit method. Now, instead, well, we evaluate f at xi plus 1, where xi plus 1 is simply x at index I plus 1. And at some point y star, and we still need to define what this y star is. And let me also note over here that I'm very descriptive in how I name these variables, which is just to make it a bit more clear and educational in these videos. I could have just as easily also simply copied this directly into this function. That would be completely equivalent and would lead to a bit less memory usage. But for educational purposes, I try to be as explicit as possible, which makes it hopefully a bit more clear to you. Whenever you're programming this yourself, feel free to do this however you like, as long as you can keep oversight of what you're doing in there. Now we still need to define what this y star is, and looking at the description of the algorithm, well, y star is the solution that we would obtain if we would have taken an Euler step from yi. So that is simply yi plus h times the Euler slope, or slope 1 in this case. Note that this is an approximation of the solution, but we do not use it directly to approximate yi plus 1 or to approximate y at index I plus 1. No, we actually only use it to compute this second slope, such that we now have this slope 1 and slope 2. We can take the average of both and use this to update the numerical solution yi and thus define the numerical solution yi plus 1. Okay, so this seems fine. Let's save it and put it to the test again. Let me call this, well, I can simply use very similar syntax as for the others. I will just call it ODE mod Euler. Again, same function f, x times y. From x is 0 to x is 2, we use h as 0.4, and we start from y at x is 0 is equal to 1. Okay, let's run it, and we see that what comes out is, well, the same x again, and logically that's something we didn't change with respect to the explicit Euler algorithm, but the y will be different. So let's also plot this. Okay. And let's have a look at the figure over here. And so here indeed we see that the numerical solutions, which are represented by the dots, so the dashes in between are just to connect these dots to give kind of a trend, but the real solutions are the dots over here. And we already plotted earlier in blue explicit Euler, in red implicit Euler, and in yellow then this is the new value for the modified Euler. And let me actually put a legend in there. So first we plotted the explicit Euler, then we plotted the implicit Euler, and finally now we have plotted modified Euler. Let me call it mod Euler. And this should put a legend on the graph as well. So that's what we see over here. Now let's take a look at which of these is actually the most accurate one. And we can easily assess that because we know what the exact solution is in this case. So we can define, well, let's define this exact solution. And for that, let me just define a closely spaced vector just for plotting reasons, that it is a nice smooth graph, x exact. And we know that the exact solution is, well, the exponent of x exact squared over 2. Okay, I made a small typo probably, yes. Okay, that gave quite a lot of output because I forgot the semicolon, but that's fine. Now let's also plot this on the graph. So x exact, y exact, and let's make this in black to stand out from the colored numerical solutions that we have. And this is what we find over here. So this data 1, let me update the legend quickly. Exacts. And then what we see over here is that, well, the exact solution is plotted in black now. And well, clearly here that even for this very coarse resolution of h is 0.4, in reality you would take a much smaller h. But even for this very coarse resolution, the modified Euler seems to be quite accurate. It's much closer to the actual solution than explicit Euler in blue or implicit Euler in red.